Now, occasionally when we're looking at torsion and torsion problems, we may come across shafts that are not circular. It's not super common, but it can happen uh, when we're twisting shapes that maybe aren't meant to be twisted or aren't naturally circular. So the big problem that we have with these non-circular shafts is they're not axis symmetric. And axis symmetric is just a very fancy word, but it's really just the word axis and symmetric basically smushed together. It's kind of fun to say, axis symmetric. Axis symmetric, like a circle is. So a circle is axis symmetric, which just means that, you know, if I put an axis anywhere, whoops, as I avoid the center here, anywhere that goes through the center, if I put an axis in, it's symmetric about that axis, right? So our circle, if I could draw a little better, you would see that no matter where I put a line that goes through the center, it will be symmetric about that line. But if we have something like a square, sure, a square is axis symmetric if I do it just vertically, like a y-axis, or if I do it just horizontally, like an x-axis. But what if I do something weird where I take it and cut it like this? It still go through the center, but now I have this whole portion up here that is not symmetrical to this portion down here, right? It does not create a nice mirror image. So this is not axis symmetric. Similarly with a triangle, let's say this is an equilateral triangle. Sure, it's axis symmetric if I go straight down the center here, or down through any of these midpoint to tip locations, right, going through the center. But as soon as I draw a line that does not hit in that same way, right, goes through the center, no longer axis symmetric, right? So these are not axis symmetric, whereas circles are, which make them really, really nice for our calculations. And what we end up with instead with these non-circular shafts is really, really complex shear stress distributions. Because as we said, when we were twisting something, when we're putting something in torsion, it kind of twists into this helical shape. And so we take some rod and we twist it, and we kind of get these helical lines. Helical lines of twist. The helical, and then it, you know, goes over the back there, and then it spins again, kind of like a barbershop pole, or a candy cane. You can imagine the way a candy cane is striped is helical, and so that helix kind of curves around. It's that whole idea of twisting. That peppermint stick is really just a stick that's been twisted of red and white together, right? But if we do that with a square, you can see the helix a lot better, but it ends up in this really weird deformation shape. And so you kind of have like it goes back that way, and then it kind of like it comes up and like twists over into itself into this odd, almost braided looking type of shape. Right? So it forms this more like a kind of like a breadstick twist. I guess you can think about with a square cross section. So this deformation really isn't very nice to measure or work with. So it's a lot more complex than what we're going to get through in this class. I just want to show you that we do have some shortcut equations. So we can calculate the maximum shear stress. I'll write this down. The maximum shear stress. This is the important part, I guess. The max shear stress occurs at edge closest to centroid. Closest to centroid. So what does that mean? The edge closest to centroid. For a square, it's going to be this area right here, this point right here. These points that are closest to the center of the shape. Right? For a circle, that's everywhere. Every point is equally close to the center of the shape. But for a triangle, it's going to hit right in these midpoints through the long edges there. Right, so the max shear stress occurs at those edges closest to the centroid. And what that allows us to do is use a nice little shortcut equation so that we can calculate the shear stress, the maximum shear stress, I should say. We won't be calculating it at any other points. But here's our little table, I guess, for some standard non-circular shafts. You could have a square, equilateral triangle, or ellipse. Not eclipse, ellipse. An ellipse. And these are our shear stress equations. And then these equations to the right of it would be our angle of twist equation. So these are just some basic rule of thumb equations that we can use when we want to do a quick and dirty shear stress calculation for an odd-shaped shaft. So we'll go ahead and look at an example using these equations. So for this example problem, we're looking at a triangular shaped shaft, and we want to know the largest torque that can be applied if the allowable shear stress is 8 ksi and the angle of twist is restricted to 0.02 radians. So again, we're seeing a problem where we have two separate restrictions being applied, which means we need to go through and do two separate checks to see which one is limiting. Possibly our shear stress is limiting or our angle of twist is limiting. So we're going to go through and check those things to find the largest torque, that T there on our shaft. And then it asks us this separate question: how much torque can be applied to a circular cross-section made of the same amount of material? Right? So if instead of making it triangular shaped, let's make it circular shaped, how much torque could we get out of this exact same amount of material? So let's go ahead and go through and find what our torque would be for this shaft given these restrictions. So our two restrictions here are torque max is 8 ksi and our angle of twist max is 0.02 radians. So again, because this is a non-circular shaft, we have to use those special equations, right? Those special equations that we found. Nope, that's our formula sheet. Here they are for our non-circular shafts. So for an equilateral triangle, this is going to be 20 times torque over a cubed. A is just the side length of the equilateral triangle. I'm going to write that down. So our 8 ksi is 20 times the torque over a cubed. And a is just that side length. So 1.5 inches cubed. And this one, I can pretty straightforward. Just rearrange a little bit and solve for torque. And I'm going to get 1.35 kip inches. 1.35 kip inches. So that was easy enough, right? Just plugging and chugging, basically. Let's go ahead and look at my angle of twist equation for the equilateral triangle. 46 TL over a to the fourth g. So 0.02 equals 46 t times the length. Length is 4 feet. I'm going to go ahead and convert that to inches. So that's 48 inches over a to the fourth. Again, a is just the side length of the triangle. 1.5 inches to the fourth times g, which g was not given to us, but it does tell us it's made of 6061 T6 aluminum. So we can open up our handy dandy properties of materials table, look up aluminum, here it is, aluminum 6061 T6, and find our modulus of rigidity. So our modulus of rigidity right here, 3.7 times 10 to the third KSI. So 3.7 times 10 to the third KSI. Again, I've got all the ingredients. All I need to do is plug and chug in my calculator. So I put everything in and I get 0.17 kip inches. 0.17 kip inches. So my smaller torque, again, is going to be my limiting factor. The smaller torque is limiting. I can't do the larger torque because then it would surpass my angle of twist. So this smaller torque is limiting. The torque has to be 0.17 kip inches, or I guess if you want to convert it, pound inches. 170 pound inches. Doesn't really matter. Either way is fine. So that would be the largest torque we could apply to this triangular shaft. That's the first part. Now we want to see, well, what if it was a circle? Taking this exact same amount of material, let's leave it as the same length, right? Be consistent in the length. All we're doing is changing that cross-sectional area. Instead of a circle, convert this triangle into a circle. Same amount of material. So that tells me that the area of my circle, that cross-sectional area, is made of the same material as the area of that triangle. So if I wanted this to be a circle, IR squared, then I would need to look at my area of my triangle here. 1/2 base times height. An equilateral triangle has 60 degrees in all of its corners. So if I wanted this length here, I can just do sine 60. 1.5 sine 60 to get that length. Or I guess it would be 0.5 or 0.75 sine 60. Right, this length here. Or opposite. Oh no, I'm using opposite over hypotenuse. Sorry, that's right. Opposite over hypotenuse. The hypotenuse is 1.5 because it's an equilateral triangle. So 1.5 sine 60. Punching in my calculator to solve for R. We get a radius of 0.56 inches. So now what we can do is we can compare how much torque we were going to get using our torque equations. Okay, so we have that max shear stress equals torque radius over J, and we have the angle of twist relationship of torque length over JG. So again, we would technically need to test both of these to find out which one is the limiting factor. But because we had the angle of twist being the limiting factor for the triangular one, there's a pretty good chance that our angle of twist is still going to be the limiting factor, even if it's a circular shaft. So if we were to go through this calculation, I'll just tell you that the shear stress method gives you a torque of 2.7 kip inches. But our angle of twist is actually the limiting factor here. So our torque would be our angle, 0.02 radians, times our J, which is pi over 2, times 0.56 to the fourth, times G. G value is still the same, 3.7 times 10 to the third KSI. all over the total length, 48 inches. All I did was rearrange this equation to solve for torque. And I get a torque of 0.23 kip inches for my circular shaft. So as you can see, this is another big reason we really like circular shafts. We can get more torque out of them, right? So this exact same shaft, if we would have just made it a circle, not only is a circle really convenient because it's axisymmetric, and because we can use it to rotate things, it's even on all sides. It slides nicely into other shapes, but it's also just more efficient. You can get more torque out of a circular shaft than you can out of a triangular shaft. So this is a big reason why we default to these circular shafts, why we're going to see them way more commonly than non-circular ones. But it still can be good to know, especially if you don't want something non-circular rotating, can be good to know how we approach these calculations for non-circular shafts.